faithfully convey, value, and interpret great books from around the world. Hello, this is Sally's Book Talk. I'm John Fan, today's interpreter and also the narrator of the voice you're hearing now. Today we'll interpret the book Feynman Lectures on Physics, the introduction. The author, Richard Feynman, was a physicist born in New York, an American of Jewish descent. Feynman is regarded as the most brilliant theoretical physicist since Einstein. In the 1940s, he developed new theories, formulations, and computational methods for quantum electrodynamics. For this contribution, Feynman won the Nobel Prize in Physics. He joined the Manhattan Project, helped develop the atomic bomb, and later investigated the Challenger space shuttle disaster, uncovering the truth behind the accident. Feynman was no bookworm. He was cheerful and outgoing, with hobbies like playing bongo drums, sketching, cracking colleagues' safes, and visiting strip clubs. His Portuguese was fluent enough to lecture at the Brazilian Academy of Sciences, making him truly unique among 20th century physicists. These eccentric stories earned him considerable public fame. In Feynman's own view, his most important academic work wasn't quantum electrodynamics or other major theoretical contributions, but a textbook, the Feynman Lectures on Physics. This book comes from his lectures to freshmen and sophomates at Caltech. Though intended for undergraduates, it's still quite challenging, don't you think? You can tell because later on, fewer undergraduates attended while more graduate students and professors showed up. Today, we're interpreting Feynman Lectures on Physics, which selects 6 original chapters from the first volume of the lectures, essentially a guided introduction. These chapters were transcribed from actual recordings, preserving Feynman's teaching style, even if not verbatim, making them highly recommended. Even if you don't grasp everything immediately, you'll get close to this physics master and explore the most accessible part of Feynman's work. The first chapter is called The Principle of the Laws of Motion. So, the chapter's introduction briefly explains one key idea. Physics differs from mathematics. Mathematics begins with axioms or rules, then deduces results within those rules. But physics can't work that way. Physics observes objective nature, and in modern physics, such observation requires expensive equipment. But at its core, it's still observation. Based on observation or experiment, we derive laws that are neither complete nor precise. According to philosophers, that's incorrect. So what can you do? You just have to learn it first and later abandon it for laws with higher approximation. For college students, the former example is Newton's laws of motion, while the latter is relativity. Which one do we learn first? Feynman says, learn the rougher one first. Among these rougher laws, Feynman believed the idea that everything is made of atoms is particularly valuable. It's called rough because atoms aren't actually the fundamental building blocks of everything. As for why it's particularly valuable, it's because at the atomic level, all natural phenomena are just atoms performing simple motions. Water is water, and steam is steam, simply because the same atoms have different distances and movement intensities. Water just has more constraints than steam, making it slightly more complex. Now consider water and salt mixed together. We observe dissolution and crystallization, which seems different from evaporation. But from an atomic perspective, it's still just changes in distance and binding between sodium ions, chloride ions, and water molecules. Here, Feynman doesn't distinguish between atoms, molecules, or ions. He temporarily calls all atomic scale entities atoms. A bit more complex. When carbon and oxygen atoms coincidentally meet, they bind tightly together. What happens? Light and heat are emitted. We call this combustion, which falls under chemistry. But this is actually a different process. Gas condensation, which often releases large amounts of heat, actually It emits light too, just in the infrared spectrum that our eyes can't see. Because of our sensory limitations, we artificially separate chemical and physical reactions. But to Feynman, it's all the same thing, moving to greater complexity, from violent scents to clouds and rain to every one of us. All can be described by organic chemistry, meteorology, and biology. But regardless, you can certainly discuss all these through atomic motion. As mentioned earlier, the atomic perspective is, after all, rough and can't solve too many problems. So far, physics aims to describe seemingly very different things with the simplest laws to reduce the variety of phenomena. Nature's like playing a huge game of chess with only a few simple rules. If you don't know the rules, it looks baffling at first, but after watching a while, you'll eventually spot a few obvious rules and then maybe more, until finally you understand all the rules. Following this approach, let's trace the path of physics development and discuss what physics does. Feynman divided the development of physics into two main stages, with 1920 as the boundary. Before 1920, humans recognized 92 different elements interacting in Euclidean three-dimensional space and uniformly flowing time. These forces were nothing but gravity and electromagnetic force, with the electromagnetic force being very strong. If two grains of sand are 30 meters apart, the charges they contain can produce a force equivalent to millions of tons. The gravitational force between these two grains is tiny. Back then, it was known that shaking a stationary charge suddenly expands its influence to distant places. Moreover, this propagation detaches from the charge and becomes an independent entity called electromagnetic waves. Around 1920, physics underwent a revolutionary shift with the emergence of relativity and quantum theory, changing people's worldview. First, time and space are no longer independent. Then gravity gets mixed in, becoming part of space-time. This was a discovery in the large-scale world. In the microscopic world, it was found that tiny particles behave unlike anything else we know. If you only know gravity and not much about electromagnetic theory, wouldn't you think there's nothing wrong with electrons orbiting the nucleus in circles? Because it's too similar to planetary motion. But Maxwell's equations show that electrons spinning that fast would instantly radiate energy as electromagnetic waves and crash into the nucleus. So either Maxwell's equations are wrong, or we must assume one thing. A particle can't have both a definite position and definite momentum at the same time, known as the uncertainty principle. Although the uncertainty principle defies common sense, it perfectly resolves issues like atomic stability and non-zero ground state energy. Importantly, it doesn't conflict with classical electromagnetic theory, but combining them creates quantum electrodynamics. As Feynman put it, we know everything outside the nucleus that currently aligns with QED. No exceptions yet, but inside the nucleus, oh dear, inside is tricky. We hope to apply known external theories to guess what's happening. Since charged particles connect through photons, we deliberately searched for a similar mediator between neutrons and protons. The result? Cosmic rays revealed about 30 new particles. What purpose do these unrelated particles serve? We hope they're different manifestations of the same thing, but our current understanding remains rough. We can only name and categorize them. Their interactions aren't too complex, though, just 4 types total, ranked by strength. Strongest is the strong interaction, what we typically call nuclear force. Physicists don't fully grasp it, but know it's 137 times stronger than electromagnetism, which ranks second. If you understand electromagnetism as charge-to-charge interaction, in particle physics, try imagining it as charge interacting with photons. Then photons act on other charges. This part we truly understand completely. Third is the weak interaction, 1,000 times weaker than electromagnetism. This governs neutron decay into protons, electrons, and neutrinos. We only partially understand its laws. Weakest is gravity, over 30 orders of magnitude weaker. Modern physics knows gravity well, so Feynman summarized fundamental physics. Outside nuclei, we know everything except the universe's origin. You can't experiment on that. Inside nuclei, we only know quantum mechanics still applies, but haven't clarified particle relationships or how long it'll take to understand. Generally, physics means studying these two things: matter's fundamental composition and force relationships. What Feynman called fundamental physics. These fields of research are evolving and often overlap with other disciplines in certain areas, making it hard to draw clear boundaries. Therefore, Feynman briefly discussed how chemistry, biology, astronomy, geoscience, and psychology relate to physics, touching just the essentials. Chemistry is especially close to physics. Early chemistry was essentially applied atomic physics, largely confirmed through chemical experiments. Later, theoretical chemistry's foundation became quantum mechanics principles. So where's the dividing line? Roughly speaking, whether a chemical reaction can occur is physics domain, the rules of the chess game, but the reaction's direction, speed, and products belong to chemistry, equivalent to the player's strategy. Yet more physicists later enjoyed intervening at this level, a trend extending to biology and even higher level strategy. From physics perspective, neural conduction in organisms is essentially a relay of ion migration. Muscle contraction involves assembly and disassembly of complex molecular components, just chemical reactions, ultimately physical processes. But the strategy here is more advanced. Another close relative is astronomy. Its early observations directly led to classical physics. Modern physics, conversely, analyzes stellar composition and evolution, though people imagine stars as handsome or charismatic figures. Feynman said stars are furnaces. Our planet and we emerged from their cooled ashes. The topic then shifts to geology. Actually, we know less about Earth than the sun. Our understanding of volcanoes and earthquakes remains rudimentary. Earth has internal circulation, but nobody can calculate it. Theoretically, these are classical mechanics problems, not profoundly complex. Another unsolved issue is atmospheric turbulence, also a classical mechanics problem. Surprisingly, we still can't compute it either. So, facing meteorology, Feynman clearly had little to say and instead discussed psychology. How does the brain learn? What changes occur in brain cells? Unfortunately, we completely don't understand these matters, only sensing similarities with computers. As for truly understanding human behavior from this direction, it's still too distant. Among all these disciplines, physics has a unique feature. It doesn't concern itself with history, while even basic chemistry always considers reaction directions. And so far, we've never believed that the laws discovered in physics change over time. Feynman thought there was no need to remain so aloof and maintain such strict barriers with other disciplines. The creation of academic classifications is merely a convenience due to limitations of our minds. Nature doesn't operate this way because the physical world encompasses thermodynamics, organic chemistry, biology, and optics. Nature probably has its own simplest arrangement, meant to make us happy without overcomplicating things. And in physicists' quest for laws, they've also discovered many valuable concrete facts. Some concepts and topics have become core to physics. The book, Feynman Lectures on Physics, selects 3 representative topics: energy, gravity, and quantum behavior, each approached uniquely, accessible to non-physicists, yet surprising for professionals. How did Feynman achieve this? First, let's hear his analogy for energy. An analogy. When talking about energy, you might think it relates to motion and vitality. If you've had STEM training, you might even calculate it. Few people claim they don't know what energy is. But Feynman said that in modern physics, we don't actually know what energy truly is. Take mischievous little Dennis. He scatters his 28 blocks everywhere, outside windows, in small boxes, in fish tanks, etc. To count them, Janice's mom searches everywhere, weighing unopenable boxes and measuring water levels in bathtubs. Thus, the block count appears as weight or height, entirely different forms. We find quantitative relationships linking these forms, just like with different energy forms. But beyond this experimental quantitative relationship, you couldn't describe any other connection between kinetic and potential energy. And because kinetic energy is defined by velocity and mass, there's no hidden entity like blocks behind it. Um, Potential energy is the same story. With energy, we can only know what it does, not why it exists. However, even answering superficial quantitative questions has produced ingenious arguments. One such argument: among all machines with identical functions, reversible machines have the highest efficiency. Tracing this concept's origins, we can almost smell the coal smoke of its era. The Industrial Revolution birthed various power generating machines. Among these, people discovered heating gas could push pistons to perform work. Conversely, pushing pistons could heat gas. In these reverse processes, some operations could undo the effects of forward operations. We call such machines reversible. Those that can't undo effects are irreversible. So Feynman's argument goes like this, right? Connect two machines, one reversible, one irreversible. First, run the irreversible machine forward, then run the reversible one backward to prove reversible machines are most efficient. Using proof by contradiction, assume irreversible machines are more efficient. Then the combined machine becomes a perpetual motion device, impossible by established principles. Analogy: Alice buys 2 coffees with 1 coin, while Bob buys only 1. Conversely, Bob exchanges 1 coffee for 1 coin, but Alice can't exchange coffee for coins. This makes Alice an irreversible machine. Okay, first have Alice spend 1 coin to buy 2 coffees and let Bob take 1. Then Bob exchanges his coffee for a coin externally. Alice uses that coin to buy 2 more coffees. This cycle continues. Same coin, endless coffee, like perpetual motion requiring no energy. Thus we see the flaw. Alice's coin is more valuable than Bob's. See? This proof by contradiction demonstrates reversible machines' maximum efficiency. This conclusion might seem trivial to some. Remember, during the Industrial Revolution, humanity suddenly believed they'd gained dominion over nature itself. Physicists' arguments at least showed inventors and engineers to remain humble before nature's laws. Energy has another mysterious property. In quantum mechanics, time symmetry leads to energy conservation. In plain terms, if a physical process can run backwards in time without altering physical laws, it implies energy conservation. These two things seem completely unrelated. Though we all know this, but connecting them is utterly mind-boggling. Of course, it's another thing we can confirm without understanding why. If this confuses you, don't feel ashamed. Detailed explanations are in Volume 3 of Feynman's Lectures. Many top students at Caltech gave up before reaching that point. Gravity is relatively straightforward. Its mathematical simplicity amazed Feynman. But like energy, there's no reliable explanation for gravity's underlying mechanism. Recall gravity's discovery. Astronomy revealed stars making near-circular motions with varied explanations, but no gravity concept existed since Newton's laws were unknown and force played no role in curved motion. Nobody found it strange. Later, Galileo found that without interference, objects would move in straight lines at constant speed. Newton then defined this interference explicitly. It's force. Planetary paths deviating from straight lines indicate force. Kepler's law states that planets sweep equal areas in equal times with the sun at center. This convinced Newton the force deflecting planets points precisely toward the sun. Not angels pulling planets, as legend said. Now force direction connected two entities. this force was generalized, any two objects connected by a straight line experience such force. Newton declared this force innate, with no why. Gravity also has puzzling properties. First, why is gravity so weak? Is it related to the universe's age? Second, what's gravity's relationship with mass? Another question. After relativity corrected Newton's gravity, might it need quantum-compatible adjustments? These are the universe's most fundamental questions, still unanswered. Now, let's set gravity aside and see how Feynman describes quantum behavior. Microscopic particle actions. Quantum behavior resembles neither waves nor particles. Physicists abandon comparisons, again admitting we can only answer how, not why. Feynman's explanation of quantum behavior is universally acclaimed as a classic. He used just a few concepts to bring us to the core of the quantum mystery. He designed a double-slit interference thought experiment. The setup includes a particle source, a barrier with two parallel slits, and a detection screen at a distance. Particles like bullets, passing through the slits, form a smooth probability distribution on the screen, dense in the center and sparse on the sides. If it were mechanical waves, like water waves, passing through such slits, the outcome would differ, forming a striped pattern of alternating strong and weak intensities on the screen. We know this is interference behavior. When we switch to electrons for this experiment, interference fringes also appear. Feynman wanted to observe exactly how the electrons pass through these two slits. Strangely, when he clearly observed the electron's path, the interference fringes vanished. When he didn't observe the path, the fringes reappeared. This shows that the act of observation itself affects the electron's path. Just because we took an extra look, the electron went off course. The final conclusion of this thought experiment is that quantum behavior has inherent uncertainty. A particle's position and momentum cannot be simultaneously determined. Quantitative analysis shows that the product of these uncertainties is about the size of Planck's constant and cannot be smaller. Of course, this is already tiny, on the order of 10 to the minus 34, but if this uncertainty, quantum mechanics would collapse. Fortunately, quantum mechanics, though full of risks, exists precisely as Feynman said. Later, people actually performed this double-slit interference experiment with real equipment. From Professor Murley at the University of Milan in 1974 to the University of Nebraska team in 2012, they repeatedly reproduced Feynman's idea in more direct ways, proving his 1962 classroom description was spot on. We can't time travel back to the 1960s to experience his unique flamboyance and unconventional humor. Luckily, those invaluable lectures have been preserved in book form to this day. Over 50 years later, the Feynman Lectures on physics haven't lost any brilliance or clarity. We can still feel sparks of wisdom and deep insights within them. Understanding how physicists view this world. Feynman said that learning to appreciate this marvelous world is a truly vital part of modern culture. As the world grows more complex, it becomes even more fascinating. Okay, that concludes our interpretation of Feynman Lectures on Physics, the Introduction. Reading notes are below the audio. See you tomorrow.